Morozova, to the right.
Okay, no problem.
She's with Ionospheric space weather from the sun to the infrastructure. She thankfully jumped into someone else's spot who needs to cancel, and we are really very thankful. And because it was on a very short schedule, and to produce such a big presentation is not that easy, so really very
Thank you
thankful.
for inviting.
Yeah, then we go on, and you can have your break whenever it's up to you. We wanted to have it between around 4 and 4:30, I think.
3:30.
Or 3 and
Yeah.
4.
We'll
Yes.
okay.
Okay. So, I forgot something, but I will tell you later. Okay, so please.
Thank you.
Maybe you tell us a little bit about you. Yeah, no, I know that you're in origin from St. Petersburg.
Yeah, but I live and work here in Portugal for already about 16 years.
16 years. So
I'm kind of Portuguese.
a long time, yeah.
Yeah, and I work in the area of space weather, and for the last something like 10 years, I'm working about in the ionospheric physics. Do we have someone working in or somehow related to space weather? Oh, so many. So, well, I hope you are not going to be bored during the lecture. Maybe you'll find something new, because space weather actually is a wide area, and there are many things, maybe, I hope, you'll know from this lecture. So, solar and geomagnetic activity, which is in short called space weather, they are main drivers of the many things, including ionospheric perturbations. And these ionospheric irregularities, they can affect our life in a very drastic way. So that's why we have to study them and to understand what, why, and how to protect from or to take care of consequences that can arise. So during the first half, so we are going to talk. I'm going to talk about space weather first in general, what's the origin, what are consequences, and then during the second half, we will talk more in detail about the ionosphere, ionospheric space weather, and economic impacts. So for the space weather, we'll start from the sun and go gradually to Earth, to the ground. And so, as I already said, space weather is short for conditions on the sun, in the interplanetary media, in the upper atmosphere, in the Earth's magnetosphere, that all affect our life and our space or ground-based technologies. Sometimes this area called heliophysics as well. Sometimes people say that space weather is when it's applied, and heliophysics is when it's more about physical studies. But I'm not sure I like this distinction. But sometimes you can hear the term heliophysics, and it's about the same things as space weather. So there are two main agents in the space weather. They are electromagnetic waves, mostly emitted by the sun, and they're plasma and particles. Most of these plasma and particles emitted by the sun, but also there are extra sources for the particles. So let's start with the sun. So I hope everyone knows that most of the energy emitted in the sun is made in its core, then it's transmitted upper through the radiative zone and then the convection zone. Well, the names are quite self-explaining. So here we just have radiation, very slow process, and here we have convection of the plasma. Then it reaches the solar surface and goes up to the solar atmosphere. Solar surface, what we can see with our naked eye, is called photosphere. So photosphere is the visible surface of the sun and the lowest part of solar atmosphere. It has temperature about 6,000 Kelvin, and there are a lot of strong magnetic field of very complicated structures. Above photosphere, there is a chromosphere. In chromosphere, temperature rise up to 10,000 Kelvin, and we can see magnetic field lines making loops or open magnetic lines. And plasma flow from the surface to the atmosphere along those loops. And above the chromosphere, we have solar corona, which is upper part of the solar atmosphere with temperatures of 2/10 million Kelvin, and it's gradually changed to solar wind. What features we can have on different areas of the solar atmosphere that can be related to solar activity? In the photosphere, we have dark sunspots. If you look at the photo in the visible light, we can sometimes see dark spots, and this is sunspots. And if we look with a high resolution, we can see that the solar surface is constantly changing, like bubbles in the boiling water. They rise, goes, change. This is called granulation. In the chromosphere, we have bright pledges. We can have sharp structures called speculoos, and we can have prominence and filaments, which is the same stuff. Filaments seen on the visible on the solar disk as a dark, curvy lines, but if they go close to the limb, we can see mostly loop-like structure, but sometimes they erupt and go from the solar surface, and this is called prominences. So depending on how we see them, we call them different names. And then finally in corona, we can have coronal loops, magnetic field lines form loops. We have solar flares, like for example here. We can have coronal mass ejections, which are chunks of plasma that goes from the sun to the space. And we can have coronal holes seen as a dark spots in the solar corona. And talking about space weather, we mostly focusing on these three things: on the flares, coronal mass ejections, and coronal holes and regions around them. Everything on the solar activity is driven by the magnetic field. Sun has magnetic field. It's created in the convection zone, and it has a very complicated evolution through the time. How we measure solar activity? The oldest index is the sunspot number. People just look at the sun and calculate the numbers of the sunspots. This plot below, it doesn't show the number, but the area taken by the sunspots at different time interval, different, I think it's monthly data here. So we see that sometimes sunspot took a lot of solar surface, and sometimes there are almost no sunspots, or there are no sunspots, sometimes completely no. And this is called sunspot cycle. It's about 11 years long. I suppose most of you already heard about 11-year solar cycle. It's actually from 9 to 16 for the period that we sure have good sunspot data. But in average, it's about 11, I think 11 and a half years, something like that. And during this solar cycle, the sunspots, it's not just change in the number. They change in the location of their appearance. In the beginning of the solar cycle, the sunspots tend to appear at latitude about 30 degrees in both hemispheres. But with progression of the sunspot cycle, they tend to appear closer to the solar equator. And they, oops, sorry.
Just ease it in the middle.
Okay. Shouldn't touch it. So if we plot not just number of the sunspots, but with their position, we can see here this diagram, which is called butterfly diagram. The position and the area of the sunspot during the progress of the solar cycle. It's also this way it's one of the ways to define when the new cycle started. Because when we have the end of the old cycle, we have sunspots close to the equator, and then there may be months without sunspots. Sometimes it appears again near the equator, and then suddenly we have a sunspot in the higher latitude, and we know new solar cycle is beginning. As I already said, everything is driven by the solar magnetic field. And the actual solar cycle is not 11 years long, it's 22 years long. Because every cycle, we have switch of the magnetic field polarity of the sun. This plot shows the magnetic field polarity for several cycles. And you see that every cycle has a dedicated polarity of the magnetic field measured in the polar latitudes. And somewhere in the middle of the cycle, there is a change, the switch of the polarity. It's also not only the polar magnetic field, not near the poles, but also the magnetic field of the sunspots. The leading sunspot has different magnetic field polarity each year. So you can see the color change. And there are theories how it's created, why it's all like that. In the beginning, we have a, okay. So in the beginning, we have a colloidal magnetic field, which is kind of wound up around the sun because of the differential rotation. In the equator, sun rotates much faster than in the poles, so it's kind of wind up around, and then there is a reconnection and change of the polarity. So about the features of the solar activity that related to space weather. First is the flares. What is flare is an electromagnetic emission. So it means that it's propagated with speed of light and can reach us in about 8 minutes, very fast. And if it happens only in radio, we call it radio bursts. If it's in visible UV or X-ray, we call it flare. Also, flare can be accompanied by a flux enhancement of the solar energetical particles. It's a solar particles, part of the solar plasma that is erupted together with during the flare. It's not just electromagnetic emission, but also can be a flux of particles. Here are examples of some flares with different magnitude. To classify solar flare, we use alphabetic and numbering classification. C flares is the smallest flare, then goes M flare, and the X flares are strongest flare, and also we have number codes for them. And this image shows the same flare at about, some of them not at about the same time. Here, I think this time, and these three at a bit earlier. They show this flare in different wavelengths, from the ultraviolet to almost X-ray. So you see it's a very energetic process. There's a lot of electromagnetic waves and some particles that leave the sun and goes to the space. Now the next thing is the coronal mass ejections. Coronal mass ejections is the ejection of the mass, solar plasma mass from the corona. Here in this animation, you can see how it's make a loop and then it's erupt from the sun. And here, so it was started and then goes there. There can be, this plasma chunks may have speed from 5,000 to 500 to 3,000 kilometers per second. So sometimes they can reach Earth even less than 1 day, and sometimes it takes 2-3 days for them to reach. And sometimes they are accompanied by flares, or flares accompanied by coronal mass ejections. Sometimes they happen without. And also what is associated with coronal mass ejections are fluxes of the solar energetic particles. Here on this image, you can see this white noise. This white noise is made by energetic particles emitted by the sun that reach this instrument and make all this noise appearing. So, and the final is coronal holes and rotating interacting regions. Most of the coronal holes took place near the poles. We see them as dark areas on the solar surface or images of the corona. They are related to the open magnetic field lines. So here we have loops, so plasma goes from lower part of corona up to corona and back. But here, plasma leaves sun. And that's why we can see them as dark areas, because what we see is deeper areas of the corona, which are cooler, so that's why we see them as dark areas on the sun's surface. Okay, question about the sun. Good. Now we leave sun and goes to the interplanetary medium. And in the planetary medium, we can have what's left sun. We have electromagnetic waves, normal electromagnetic waves, flares. We have energetic particles emitted by the sun during some eruptions, or steadily going constantly solar wind. Solar wind is a flux of solar plasma that leaves corona and go to the space. And we also have just energetic particles emitted by the sun and galactic cosmic rays, which I'm going to talk a bit later. So solar wind. Solar wind is a continuous flow of the plasma from the sun, mostly made from electrons, protons, alphas, and tiny bit of anything else that could happen in corona. The energy from units to tens of kiloelectron volts, and there are two types of solar wind. Slow solar wind, that's emitted from the solar surface, and fast, emitted from the coronal holes and rotating interaction regions. Also, because solar magnetic field is what is called frozen in the solar wind. So magnetic field is brought by solar wind to the space. So we have interplanetary magnetic field. Interplanetary magnetic field lines are still connected to the sun's surface. And because everything is rotating, we have a specific shape of the magnetic field in the space, which is called Parker spiral or ballerina skirt. So it's rotating and kind of flipping around. And because of this configuration of magnetic field, we have so-called geo-effective events and non-geo-effective events. For example, geo-effective CME. It's a CME that is launched from the sun, and then when plasma goes along magnetic field lines, it can come to the Earth. So it means that they can be launched in specific areas of latitudes and longitudes. Also, they have to have a good speed to reach Earth, not to dissipate. And also magnetic field and mass and configuration magnetic field inside. So here, there are 3 examples. 2 top are non-geoeffective CVs. This tiny yellow dot here is the Earth. So here we have a CME that erupted, well, a bit too early to hit Earth. So it's erupted, and when the plasma reaches Earth after the rotation, it's already not affecting Earth in a significant way. Here, it's launched too late. It's already passing the Earth. And here is the right geoeffective CME, when it's erupted and it's come to Earth and hit it full in the face, and we have all changes in the magnetic field, geomagnetic storm, and all the fun. Solar particles, which are not plasma, they're just particle fluxes. Solar energetic particles, they are emitted with solar flares and CMEs. On this plot, the blue line is the number of flares per solar cycle. Red is number of CMEs, and green shows us the fluxes of the solar particles. And you see that they follow both CME and flare numbers. When they come to Earth, they interact with just Earth's magnetic field and also absorbed in the atmosphere. But sometimes, with a very energetic particles, we can have what is called ground level enhancement, when we have a sharp increase of the cosmic rays measured on the ground. There is a network of monitors that measure cosmic rays or energetic particles that come from the space. They are measured on the ground, and if we have this is called ground level enhancement. They are not very often, but can be visible during the high activity periods. And also, we have so-called galactic cosmic rays. Galactic cosmic rays comes from out of solar system. They come from black holes, nebulas, galactic nucleus, supernova, whatever. They are a very high energy to come all this way to us and enter solar system. And this is the maximum energy that register it on the ground, in our ground instruments. And this is the highest energy that we ever see. We couldn't make with our instruments, with our colliders or whatever, the energy this big as this number. So it's an instrument for high energy physicists to study universe, the cosmic rays. They come to solar system, and they are affected by the solar magnetic field, interplanetary magnetic field, by the Earth magnetic field if they come to us, and they're also absorbed in the atmosphere. And their intensity of the galactic cosmic rays flux is anti-correlated with the solar activity cycle. This plot is not very well aligned, but when we have a maximum of the solar activity, we have minimum of the galactic cosmic rays intensity, because Sun is filling interplanetary medium in the solar system with its magnetic field, and it reflects particles, and they couldn't in this amount as they can during the solar minimum. When there is a solar minimum, we have increase of the flux. And similar stuff can happen during geomagnetic storm. If we have if solar wind allow geomagnetic field to enhance, in average, we have less cosmic rays measured on the ground. We have an event called Forbush decrease. It's a sudden decrease of the galactic cosmic rays intensity measured on the ground. So now we go into geomagnetic field. So I suppose everyone knows that Earth has magnetic field, dipole magnetic field. And when it meets solar wind, it creates things called magnetosphere. So magnetosphere, we can see that on the sunlit side, it's a bit compressed magnetic field. And now on the dark side, it's stretched far away, making things called magnetotail. So we have compressed front side and stretched tail side. In the magnetosphere, we have a bow shock, which is a boundary between the supersonic and subsonic solar wind. Below bow shock, there is a magnetosheath, which area where we still have solar wind conditions in the conditions they are driven by the solar wind. But there is a boundary called magnetopause. This is a boundary that divide areas where we have solar wind conditions and geomagnetic field conditions. Inside the magnetosphere, below the magnetopause, inside the magnetosphere, processes driven by the Earth's magnetic field, not exactly by the solar wind. In the magnetosphere, we have a number of main current systems: magnetopause current, tail current, neutral sheet current that goes across the magnetosphere, because in magnetosphere we have a magnetic field of different polarities, and between them there is a imaginary kind of boundary called neutral sheet, where we have that separate magnetic field light of opposite polarities. So there is a current there. There is a ring current flowing around the Earth. And there are field-aligned currents. They connect the Earth's ionosphere and the other areas of the magnetosphere. Also inside magnetosphere, we have radiation belts or Van Allen belts. There are two belts of energetic particles, mostly electrons, that constantly flow around the Earth. Okay, this is a small
In this visualization, Earth's magnetic field structure is represented by lines that correspond to the paths charged particles would travel close to the Earth. The Sun's magnetic field, carried in the plasma of the solar wind, flows continuously by the Earth, distorting the planet's field and pulling it back into a windsock-type structure. The red illustrates the higher density plasma, which forms the magnetopause, the boundary between the magnetic influence of the Sun and the Earth. The wind also forms a lower density magnetotail behind the Earth, represented by blue in this computer model. This process is happening all the time as the solar wind is constantly flowing by the Earth. But a coronal mass ejection, or CME, can change things. The higher density plasma and stronger magnetic field carried within the CME strikes Earth's field and significantly alters the structure. Here we see the dramatic changes in Earth's magnetic field and the shape of the magnetopause as the CME passes Earth. But close to Earth, the magnetic field is largely unchanged. Earth is protected from the intense solar event. This is the case for a rather ordinary CME. In this example, a CME launched by an X3 flare from December 2006. But what would happen in the case of a more intense event, such as the Carrington event of 1859? With the aid of similar computer models as before, we can explore some of these possibilities. Here, a much stronger CME compresses the magnetic field between the Sun and Earth and generates more density in the bow shock, represented by darker red. The front of the magnetopause is pushed much closer to the Earth than usual. Even the field and plasma trailing behind the Earth are more strongly distorted.
Carrington event? No. Did you ever heard about the Carrington event? Carrington event happened in the last 19th century. And it was, I think it was it can be called the first space weather event because it's affected infrastructure. I suppose, well, during this, there was a flare. Actually, it was the first flare ever recorded because we have a lucky amateur astronomer, Carrington, who observed sun and he saw the bright area on the sun. And it was the first recording of the solar flare. And then a couple of days later, there was a huge geomagnetic storm. Most probably, well, we already had some magnetometers. Already there have been some observatories measuring magnetic field, but unfortunately, we still don't know how exactly strong this Carrington event was, because in some instruments, they just go away from the paper area, and we don't know exactly. There are some estimation how strong it was, but we still don't know how exactly. And it was affected infrastructure of the day. Mostly it was in America, there was a very highly developed telegraph system. And during this geomagnetic storm, in some areas, telegraphists could talk to each other without their instrument connected to the batteries. So there was a current in the system that provide all the connections. Some unlucky, received damage from their instruments, but so it was the first space weather event when conditions of the sun affected us on the ground. And of course, there was some auroras visible in the very low latitudes. So, geomagnetic storms, that's what happened. What is geomagnetic storms? It's a disturbance on the magnetic field. That's produced by intensification of currents in the magnetosphere. Magnetosphere changed its shape, as we already saw, and currents intensify and produce changes of the magnetic field, measured also on the ground. So its main phase can last some hours, and the recovery may be days. Sometimes we have small storms that last one day. Sometimes we have longer storms that maybe some 2 or 3 storms in one after one. And so it can take days or maybe a week to recover to the quiet condition. The origin of the geomagnetic storm is solar wind. When in the solar wind, we have specific conditions, like solar wind vertical component of the magnetic field is what we call southward directed. If it's southward directed, it has opposite direction to the Earth's magnetic field. And when we have a magnetic field of opposite polarities close together, we have things called magnetic reconnections. So there are, for example, there are some inhomogeneities, and they push it too close, and then there is a reconnection. And reconnection is a process of release of huge energy. So particles goes from the reconnection point in opposite direction, and also it means that the magnetic field is kind of compressed, made close to the Earth, and the magnetic field increase in this area. Main sources of the geomagnetic storms are coronal mass ejections and streams from coronal holes or sea airs. Also, during geomagnetic storms, we can have auroras, mostly in polar latitudes, but sometimes these are strong storms. I think last year there was some storm visible even in middle latitudes. Aurora were visible. To measure geomagnetic field disturbances, we have several indices. One is very widely used is a disturbance storm time index, or DST. It's calculated using measurement of the horizontal magnetic field at several stations located close to equator. And this variation of the DST mostly related to the ring current, that running around the Earth. During the storms, it intensify, and it's kind of cancel Earth's magnetic field, and we have decrease of the DST index. We also use DST to classify the strength of the storm. If we have something like minus 50 nanotesla, we can say it's a storm. If it's minus 100, it's a moderate storm. Then there is an intense storm. And if it's below minus 250 nanotesla, it's a superstorm. This is an example of a storm happens in 2003 near the Halloween season. And there was 2 decreases. The deepest reached almost minus 450 nanotesla. The problem with DST is that it's an hourly index. So now people more often use a SIM-H index. It is derived in about the same way, but it's a minute index, and it's produced using data from a bit more observatories, some of them located far from equator. In the middle latitude, we use K and KP indices. K index was proposed something like 100 years ago. And it's a quasi-logarithmic index, also computed using the horizontal measurements of the magnetic field. We remove the baseline, we remove daily variation, and then we apply a palette to define the amplitude of the geomagnetic field variation and classify it from 0 to 9. And it's calculated every 3 hours. So this index was very advanced when it was proposed, but now, of course, it's not very useful because, for example, we have storm minus 350 nanotesla and storm minus 450 nanotesla, but we have Kp of the same value, 9. So it's not good to have this index, and now the people developed 2 indices, H indices. They calculated every 30 or 60 minutes, and they are called open index, so they don't stop after 9. Below 9, they are about the same as K index, but after that, they can be 9, 10, 11, proportionally to the amplitude of the magnetic field. Also, there are A indices. They are similar to K indices, but they are in nanotesla. These 3 type of indices, they are used to classify the mid-latitudinal variation of geomagnetic field. And P stays for planetary. Every observatory calculated its K index, and then several observatories selected and calculated planetary average index. And if you want to study auroral latitudes and variation of geomagnetic field there, we use auroral electrojet indices. Any questions? Everything's fine? Fantastic. Now goes down to the atmosphere. Atmosphere, we can look at atmosphere in different ways. We can look at the temperature distribution, pressure distribution, density, ionization, and atmosphere is where we have the dynamics, winds, tides, waves, and with that where we have weather and climate. If you look at the temperature stratification, we can have a troposphere where temperature decrease, then a stratosphere where temperature increase because of the ozone absorption of ultraviolet. Then in the mesosphere, the temperature starts to decrease again, and above certain level, we have a thermosphere where temperature rise. The difference between the thermosphere and other part of the atmosphere is that below we have a thermodynamic temperature, like particles exchange energy, and we have average thermodynamical temperature like here. But here, the air is so sparse that particles not often hit each other and exchange energy. So here, energy, temperature, is the energy of the particles. So troposphere is a lower atmosphere. Then we have middle atmosphere, which includes stratosphere and low mesosphere. And then upper mesosphere and thermosphere form upper atmosphere. If you look at the distribution of the different atoms and molecules, then below about 100 kilometers, we have a homogeneous distribution, well-mixed air, mostly 78% of molecular nitrogen, 21% molecular oxygen, and some trace gases. But below this altitude, above this altitude, we have a heterosphere where there is already a stratification. Lighter atoms and molecules goes up, and heavier goes down. And we have, at about 300 kilometers, we already have 78% of atomic oxygen, 21% of molecular nitrogen, and a small amount molecular oxygen. And also above 2,000 kilometers, we have geocorona, which is made mostly by protons. So upper atmosphere is a place for the ionosphere. Ionosphere is ionized part of the atmosphere. The source of ionization is photoionization by the solar UV and X-ray lights. Also, if we are going close to polar latitudes, we have ionization with electrons and cosmic rays. There is a coupling between the ionized and the neutral part of the ionosphere because of the atmospheric dynamics. And because it's a partially ionized plasma, it affects electromagnetic wave propagation. And this is how we found it, study it, and use it. So the ionosphere was discovered in the beginning of, well, actually the end of the 19th century, when Marconi tried his experiment of sending radio waves from Europe to America. Most people believe that he's crazy because Earth is round, and so electromagnetic wave, they propagate along straight lines, so there would be nothing. But it looks like he was extremely lucky. He chose exactly a good position, he chose a good wavelength, and he communicated between the UK and American station in Newfoundland. And it first happens in December 1901, and then next year they repeated it. And people started to thought what happened, how it can be. And well, it's actually was not the first thing that people thought about some things in the upper above them that affect, that there should be currents or maybe not, but people started to think and they said there should be a layer of some free electrons that affect radio wave propagation. It was called E layer. I'm not sure if it's for electrons or electric field, but it was called E. And it was discovered in experiment in 1924. So people sent electromagnetic waves up and found that they are reflected from about 100 kilometers. And later they discovered that above the E layer there is another layer, and this was called F layer. And then they had no other choice but to start talking about the ionosphere. So ionosphere is an area where we have a distribution of the free electrons. This is a profile of electron density with altitude. So it changes with time, it changes with season, solar activity, day, night, geomagnetic activity. It's different at different latitudes, different heights, and we have D, E, F, 1, F2 layers. And we're going to talk about in more details about the ionosphere after the break. But now, how we can study ionosphere? Ionosphere is partially ionized plasma, so it affects electromagnetic wave propagation, and means that only electromagnetic wave of frequency above certain threshold can propagate through this plasma. And if they have frequency below, they are reflected. And there is a formula connecting electron density and the frequency, which is called critical frequency. And if we have, for example, emitter on the ground, we send radio waves up, and then we have a receiver nearby, we can see when they are reflected, came back. We can calculate the altitude where they've been reflected, and knowing the frequency, we can calculate the electron density and make profile if we use different frequency to probe the ionosphere. Also, another way is to use all-sky cameras and Fabry-Perot interferometers, because in the ionosphere there is these ions and molecules, they emit specific light that can be measured. The more light, the more density of this species, and we can study ionosphere there. Also, nowadays, we can GNSS satellites that constantly flow around Earth and send electromagnetic signal. And when it goes through the ionosphere, it's affected in a specific way. There is a thing called phase delay, which is proportional to the total number of electrons in this column between the satellite and the receiver. And this parameter is called total electron content, or TEC, or TEC. It's measured in TEC units, and we can, using the GNSS instruments, we can kind of probe atmosphere and obtain this index and know how ionized the atmosphere is, how much free electrons we have in the atmosphere. Also, sometimes we have short changes in the signal intensity, phase, and this is called scintillations, and we can study these events using the GNSS signal as well. The main parameters we use to study ionosphere are, well, critical frequency, peak electron density derived from them using such formulas, height of the peak density, and if we probe at ionosphere using different frequency, we can make electron density as a function of the altitude. From GNSS, we can have TEC, we have scintillation indices, which are amplitude and phase scintillation, and the rate of TEC, how fastly TEC change with time. So, how space weather affects the infrastructure? I'm going to talk about two main agents, the CMEs, which means geomagnetic storms, and the flares. So for CMEs, we have plasma and magnetic field, and we have energetic particles. For flares, we have electromagnetic waves, and we have particles as well. And they all can affect different places in the Earth environment, from near space to the ground. So let's start with CMEs. CMEs accompanied by the solar particles, and also when there is a geomagnetic storms, there is increased auroral and radiation belt particles precipitation to the to this area, and they can affect satellites. They can cause surface charging because it's charged particles. They can go inside some instruments, and damage them. They could hit some processor or memory chips and cause them malfunctioning, cause single event effect. They can cause noise and radiation damage. And if you have humans in space, they can provide radiation damage to their DNA and radiation hazards. In the magnetosphere, we have geomagnetic storms because of the CMEs and or coronal holes. There is no particular infrastructure there, but magnetospheric storms, they affect everything that is below. And the ionosphere, we have extra ionization and expansion of the upper atmosphere. Expansion is due to the Joule heating of the, because of all the currents that flow there in the polar atmosphere, ionosphere. And if we have expansion of the atmosphere, we have things called increased atmospheric drag. The satellites flow at a certain orbit, and it's designed to flow through the atmosphere of specific density. If suddenly atmosphere expands, the satellite flowing through the more dense atmosphere, so its orbit changes and it goes down and can be burned in the upper part of the atmosphere, and so we can result in a loss of a satellite. But also because of the extra ionization, it affects communication and GNSS satellites. We have loss of log, so receiver can constantly connect to a satellite. We have scintillations and other kind of perturbations, and radio blackout in the high latitudes, where all the currents and precipitation appears, and increase of the ionization cause blackout. So people couldn't communicate using radio waves or certain wavelengths. Then in the middle atmosphere, these energetic particles, they can, if some airplane flowing through the high latitude route, normally like from Europe to America, it's easier to fly through near the poles. But during the geomagnetic storms, it's a danger area because we have precipitation of energetic particles, and it can cause radiative damage to DNA of passenger, which is not that important because we are not often flying, but for the crew and pilots, it's very significant risk of radiation hazard. And then to the ground, in the grounded conductors, changing magnetic field result in electric currents. So currents flowing through the grounded conductors like rails, cables, pipes, power grid, and for these three, they caused mostly corruption and damage, but if they have huge currents flowing through the power grid, they can result in damage of the infrastructure, transformers, power grids themselves, and they can result in a blackout, like it was in, I don't remember, 1986 or 1989. There was a huge blackout in North America during geomagnetic storms. Some power lines in Canada failed, and they've been affected also north part of the US. So people stayed without electricity for hours and maybe sometimes for days, all because of the geomagnetic storm. Flares. Flares are electromagnetic waves and energetic particles. So in the near space, of course, energetic particles have the same effect as energetic particles of CMEs, but increase of the UV and X-ray light can damage solar panels that are used by satellites and cosmic space station. In the magnetosphere, they don't have any specific effect. In the ionosphere, they cause extra ionization. And we have loss of log with satellites, installation, and radio blackout that can be seen at all latitudes, not only at polar during geomagnetic storm, but at all latitudes. And in the middle atmosphere, they may cause ozone destruction and increase of the UV flux here on the ground, but this effect is very temporal, and we are not very worried about this. And they don't have any effect direct on the infrastructure on the ground. Okay, this nice figure show practically all space weather effects that I've been talking about. And if you have questions, it's the right time for that. Ask them. Yes?
When there is storms like that, do you have any protocols for the astronauts or for the people flying also?
Yes. Yeah, there are systems, well, I think the most developed, of course, is NASA, but I think ESA as well. They have some system warning during some storms, astronauts should go to a more protected part of the space station. And as I said, it's dangerous to let airplanes to flow through the polar latitude, so the flights diverted, and it may have consequences, not just delayed flight, but it's more expensive because of the fuel and stuff. And also communication problem, and actually we are going to talk about a bit more at the end of this lecture. So, yeah.
Quick question, because when you set up tech values, EEC, there are several receivers around the world.
Now, maybe.
Yeah, so did they take the same altitude? Means you said there will be at 2 points, and they iterate the values.
Okay. Yeah. Okay. No? Yeah. So when we have a receiver anywhere on the ground, and we have a GNSS satellite or whatever orbit it is, we can calculate using the parameters of the signal. We calculate a thing what is called slant tech. So tech along the light side between the receiver and satellites. These parameters can be used by itself, because we know position of the satellites, we know position of the receiver. For example, sometimes we can even make a tomography using these parameters. But using a simple mathematics trick, we can calculate what is called vertical tech. So we kind of project to vertical axis. And these parameters is already used to create, we can average VTech for several satellites, and we have a VTech for our position, for example. We can use this to create ionospheric maps. So the ionospheric maps are created using VTech. So first we have slant tech, and then we calculate for each satellite VTech, and then we average for areas or position.
Calculation. The reading starts from 60 kilometers. 60. So the plasma is integrated, right?
Well, this parameter is integrated parameter. It's a number of electrons in this path. And it's obtained like that. It's not like we integrate something. For example, if you have a density profile, we can integrate, obtain this parameter. But using the GNSS signal, we already have this tech value exactly, because, there are a huge, complicated formula for taking care of this stuff. Of course, it's kind of approximation, but if we kind of integrate the observation from the UV ionozones, we can obtain about the same values. There are errors, of course, but it's about the same. Yes?
Okay, thanks for the presentation. So I would like to ask if there is any way to differentiate between the signatures of solar flares and the CME in the ionosphere. There is a major event of phenomena that's particular to each of these. There is
they're both very complicated things. And
I was curious in the event that we have solar flares and the CMEs.
sometimes there is a solar flare and CMEs. And actually the mechanism for most often used, well, that most often creates CMEs. And the mechanism that creates solar flares is the same mechanism, is magnetic reconnection. So magnetic fields on the sun, in the solar atmosphere, they're reconnected, and then there is a flow of plasma goes down to the solar surface, and flow of plasma goes up. If in specific condition we have only all this energy is released as electromagnetic waves, and we have flare. But sometimes it's probably strong enough to push also plasma, and we have CMEs. So it's the origin, well, there may be other sources for CMEs, but the most well-known mechanism is magnetic reconnection.
Yeah, because you talk about the atmospheric drag and
well, okay, atmospheric drag appears in the Earth's atmosphere during geomagnetic storms. Because during geomagnetic storms, as you already saw in the movie, we have intensification of the currents. And currents produce Joule heating in the upper atmosphere. And this, well, heat atmosphere and it expands. And this caused change of the, well, atmospheric drag and stuff. But solar flare, it doesn't heat atmosphere. Solar flare, when it comes, it's mostly ionize air and affect ionosphere, not producing heating. So, and heating is produced by the Earth stuff. It's caused by the solar sources, but it's produced by the Earth's magnetosphere currents.
Okay, thanks. One more question is the geomagnetic indices.
Mm-hmm.
So I want to classify, okay, there's a bias or this, which of these indices do you think you should rely on? BST, KP?
All of them. It depends on what is your purpose, what you are doing, why you need this classification. No? The first thing is that the KP and DST indices are very old indices. So that's why we still keep using them. Even though they are not very good, we know the problem is 3 hours index and hourly index. For nowadays, it's already not very good time resolution. But we still use them because we know them for century. With DST a bit less, but they are long series. So we can study old historical storms, and we use these indices to model them or classify them. So we still have to keep those indices, even if we're going to use a new one. We still have to keep those to continue to make comparison between the old one and the new one. And normally, the strength of the storm is classified using the DST, like here, this gradation. If you use KP, we also say that if it's below 4, it's quiet. If it's 4, it's moderately affected, and it's above 4, 5, 6, 7, 8, it's already a storm. But the problem with already with KP is that it's end on 9, so we kind of, the storms different in DST are the same in KP, which is also not good, but we still have to use it because, as I already said, we'll use it for many years. The DST index, mostly during the geomagnetic storms, the main phase, it reflects mostly the ring current conditions. So we study this, we kind of understand it's not only ring current because everything is related, but it's mostly ring current. For K indices, they are calculated using middle latitudinal station, so we use them to classify storms in the middle latitudes. And in the polar latitudes, we have auroral electrojet indices. There are 3 indices. And because polar latitudes are very geomagnetically active latitudes, so they change very drastically. But if you study something in the polar, this is your indexes. So,
okay. Actually, the reason why I asked the questions, I studied fossil mostly from below, earthquakes, right? So, and for you to search for signature, you have to make sure that the space weather effects are minimized. You check the DST, KPA, etc. So, but in the event that you check the DST, KPA index, and they are both below the threshold, and then let's say, okay, the reviewer said, oh no, you have to stay in this. Which we know that this makes sense, especially from high latitude, which is constantly disturbed.
well, it's calculated using high latitude station, but sometimes we see things at middle latitude which are kind of echo of the things happened in the high latitude. Even here in Lisbon, I know that some events happen during the geomagnetically quiet conditions. We have KP, DST, very low, but I can see some variation. And when I look at the IA index, I can see where it comes from because of the coupling between the high latitudes and the low latitudes.
So if you want to study an event, it's a phenomenon you have to
Of course, you start with the most possible agent, most possible cause. But then if it's not working, yes, you start detective story and trying to find something. And polar latitudes can be the source of the... Yeah. Yeah.
What is the advantage of this interaction? Is it related to the stations or just the fast density?
May I wait to answer your question to the next after the break, because we're going to talk about this. Okay? So maybe we can make a break, but before the break, here you can see a number of copies of this book. It's a free copy for you. You can pick some. It's just 10 of them. So, but if you are staying for the conference, during the conference at the exhibition, there would be booth of the ISWAN, European Space Weather Space Climate Association, where you can find more free copies of this book. Okay? So, but you can take all this. It's about space weather. It's not exactly for the general public, but for non-specialists. So you can take this book and read at your free time. So let's have a break. More emphasis on the ionosphere and stuff that happens here. So what is ionosphere? Well, we already talked what is ionosphere, but more details about physics, currents, coupling, and how specific parameters vary during space weather events. So the ionosphere, as I already told, it's made by the ionization. It's located between about 50, 60 kilometers and up to 800. Their main photoionization reaction are these. So we see that this, the more atomic oxygen we have, the more free electrons we have. And also, if we are at the high latitude, there is ionization by the precipitating energetic particles from space and from electron belts. The losses are through the recombination. Charge exchange, dissociative recombination, and radiative recombination. The most two important reactions are there. And you see that the more molecular nitrogen we have, the less electron we have. So this lead to relations between the electron density and the ratio of atomic oxygen and molecular nitrogen, the concentration of these atoms and molecular. So this is very important things to remember. So in the ionosphere, we have up to 4 layers. The lowest one called D. Above it, there is a E layer. And then during the day, we have F1 and F2 layers, which during the night combine together to form the F layer. So in the daytime, we have 4. In the night, 2. The strongest of all layers is the F layer. It's the E and F layers. They are created mostly by ionization from the solar UV and X-ray. There are also ways to ionize ionosphere through precipitation. They are also at different altitudes, but this happens only in high latitudes, and this absorption of the UV and X-ray, it happens at all latitudes, and they create E and F layers. So D layer, the lowest one, between 50 and 90 kilometers, exists only during the daytime. Why? Because the atmosphere is too dense and the recombination is too strong. It's created by ionization through Lyman alpha for NO molecules and hard X-ray for molecular nitrogen and oxygen. Above it, there is a E layer, the one that was first discovered. At about 100 kilometers, created by soft X-ray and UV, ionizing molecular nitrogen and oxygen. And also inside E layer, we have things called sporadic E layers. They kind of areas of enhanced ionization inside the E layer. Above E, there is F1 layer at about 200 kilometers, extreme UV ionizing atomic oxygen, and during the daytime, molecular nitrogen. And above F1, there is F2, the biggest layer, the layer with highest electron density at about 300 kilometers. It's created by the same photoionization process, but because it's located much higher, the density of the atmosphere is lower, and the recombination rate is also lower. So that's why we have more free electrons here. It's just because loss is much less than creation of the free electrons. Why? Well, why these layers are created? If you think about, from physical point of view, to create free electrons, we need ionization radiation and we need neutrals. At the upper atmosphere, we have a lot of ionizing radiation, but the air is not very dense, so ionization rate should be low. Near the ground, deeper in the atmosphere, we have a lot of neutrals to be ionized, but the ionizing radiation already absorbed at higher altitude, so ionization rate here is also small. So somewhere in between, there should be a maximum. And we can calculate it using very specific, very strict conditions, like monochromatic radiation, single neutral element, exponential distribution, and photochemical equilibrium. If you assume this, we can define the absorbed energies with this formula, and adding the barometric formula and having a lot of heavy mathematics, we can produce this equation. Ion production rate as a function of the altitude. As you look at this, you can see that it depends on the zenith angle. So it's changed during the time. So if the sun is zenith, the production rate is higher. If it's in the morning or afternoon, then the production rate should be smaller. This shape called Chapman layer, named after a scientist who makes this calculation and produce this equation. And if you look at the ideal condition, because ideal condition, monochromatic, single neutral, really ideal. But if you look at the ideal case and the actual atmosphere, we see that this ideal case is quite good to explain what we see. Of course, for the lowest, for D layer, it's not exactly Chapman layer because atmosphere is already too dense and negative ions with attached electrons play a role and disturb the photochemical equilibrium. But the E and F1 layers, they are truly Chapman layers, these two. If we compare measurements and theoretical calculations, we can see very good agreement between them. And if you go up to the F2 layers, it's not exactly Chapman layer because at this altitude we already have important transport processes. Bipolar diffusion, wind drifts, and electromagnetic drifts. So atmosphere change from day to night, from season to month to month, between the solar activity cycles, geomagnetic activity. It's also different at different latitudes, and you already know that it's different at different altitudes. So electron density profile. From, day-night, during the day we have 4 layers, during the night we have 2. And these plots also show the TEC variation, total electron content. It's obvious that during the night we don't have ionization, so the combination try to take as more free electrons as possible, but when sun rises, then we have ionization, we have more and more free electrons, and the peak is reached somewhere after the local midday, and then sun goes down, recombination prevail, and then we have decrease of the free electrons in the evening, in the night. Season. During summer, we have more insolation, so we should expect high ionization during the summertime than during the winter. And this is the case except for the middle latitude. At middle latitude, we have a so-called winter anomaly, when the average value during the winter months is slightly higher than during the summer months. This is related to atmospheric dynamics. And also there is a semi-annual cycle, because during geomagnetic storm, we have more ionization and higher TEC values. This is TEC. And geomagnetic storms happens more often during the equinoctial seasons, so in the spring and in the autumn. Solar geomagnetic activity. We have regular variation of the ionization because of the solar cycle. Here, this red line show average electron density during solar maximum during daytime, and this dark red shows during the night. And during the solar minimum, the blue line shows this electron density during the day and during the night. So you see there's a huge difference in the electron density variation. If we have something long living on the sun, like regions that emit regular flares, or there are some things that produce that produce geomagnetic disturbances, and these things on the sun surface are long-living, so they live more than one rotation. Then we have a recurrent change of the ionosphere because of this active regions come to view and affect Earth's magnetosphere and ionosphere. If you have flare, we have increase of the ionization. This red lines show change of the tech during a day with a flare marked by a blue line, and the black line shows the average quiet day variation. You see there is a sharp increase in the ionization when there is a flare. During geomagnetic storms, again, black shows the quiet day variation and the red actual observation during a specific day. And we have, during one day of the storm, we have an increase of the tech, and then we have a decrease on the next day, for example. Also, in the polar cap, in the polar latitude, if there is a solar flare, there is a thing called polar cap absorption, when extra ionization from the flare and the ionization of the polar D and E layers cause absorption of the electromagnetic waves that are used for communication. So there is a ionization and extra ionization, and electromagnetic waves are absorbed, and people couldn't communicate using these radio waves. Also, in the Earth's atmosphere, there is a constant lighting activity, and it's affect delay ionization, and also there are things called Whistler waves. They're propagating in these electromagnetic waves in the upper atmosphere caused by lighting activity, and they also affect polar ionosphere D layer, cause direct heating when they are absorbed and ionization. Lower areas of the atmosphere, or actually the place where ionosphere is belonging is thermosphere. In this area there are winds and tides because it's an atmosphere, and there are some local turbulence and inhomogeneities, and because of the connections between the coupling between the ionized and neutral part of the ionosphere, the number of electrons also fluctuate with these winds and these tides. Even more, if we are going to the lower atmosphere, to the troposphere and stratosphere, sometimes there are such conditions that create atmospheric waves. Gravity waves, they created, for example, when there is some orographic things that disturb wind in the atmosphere. Or there are some conditions in the tropical atmosphere. There is a huge clouds and perturbation. And these gravity waves, they can propagate in specific condition upward. And when they propagate upward, the amplitude increase. And when they reach mesospheric, thermospheric altitudes, they affect the local neutral atmosphere and ionized part, and we can see in, for example, tech variations, the gravity waves that create in the lower atmosphere, in the stratosphere and the troposphere. And also, if you have a quake, tsunami, or volcano eruptions, they also create gravity waves and other atmospheric waves. They propagate and can be seen. The effect can be seen in ionization rate or ionization electron density in the ionosphere. So in space, we expect that the highest ionization rate should be expected near the equator. And it's kind of there, but actually the highest ionization is observed in a place so-called northern and southern crests. There are areas around to the north and to the south of the geomagnetic equator. And this is also called equatorial anomaly. So we don't have a smooth increase of the ionization near the equator, but we kind of two hills with a trough between them. Also in the middle latitude, it's not very visible here, but in the middle latitude, there is a thing called mid-latitudinal trough, which is a drop of the electron density during nighttime, and it's close to the auroral ovals in the polar latitudes. So this is a very nice figure showing almost everything that happens in the ionosphere. You already see some things I've been talking about, gravity waves, some field-aligned currents, for example. So, ionosphere is a partially ionized plasma, but it's because the number of electrons and ions is about the same, so we have a near neutrality. It's created by the production of the ionization, it has its losses, but it's also, the electron density is affected by the transport process. Due to electric and magnetic fields, due to gravity, due to pressure gradients, and because of the collisions between ions, electrons, and neutrals. So in the E region, ions are affected by the Lorentz force and collisions with neutrals, because E layers is low and there are quite dense atmosphere. But the electrons, they're affected only by the Lorentz force. So their velocity are different, and we have currents. Currents flow in the E region. In the F region, there is no collision with neutrals, so the electron and ion velocity are the same, so there are no electric currents in the F region. But there is a thing called ambipolar diffusion due to gravity and pressure gradients, and they have a bit different velocity for ions and electrons. Also, if there are neutral winds, they affect location of the F region. If the winds blow poleward, ionosphere goes kind of down. If the wind flow equatorward, ionosphere goes up, F layer goes up. This process is slow and propagates in latitudinal direction. Also, we have electric field. Different direction of the electric field affect position of the F layer. If the electric field is westward, F layer goes down. If it's eastward, it goes up. And this can happen during geomagnetic storm when we have changes of the electric field. This process is very fast, it's global and simultaneous, and it's important during geomagnetic storm. That's one of the important processes of the ionosphere development during geomagnetic storm. There are three main currents flowing in the ionosphere. Solar quiet currents in the middle latitude, equatorial electrojet near the equator, and auroral electrojets in the polar regions in both hemispheres. And this electrojets are responsible for, because they are connected to the field-aligned current, and so they are responsible for connection between the polar ionosphere and magnetosphere. So SQ current, solar quiet, it's created by ionospheric dynamo. So during the daytime, we have solar photoionization, but we have magnetic fields and we have currents. They flow in E region, of course. There are two vortices in the north and the south hemisphere. In the north hemisphere, it's counterclockwise. In the south hemisphere, it's clockwise directed. And this creates a small current along the equator. And actually, these currents are perceived when people observe the geomagnetic field variation measured on the ground. If you look on how from day to day geomagnetic fields vary at the ground level, we see that there are, for different components, there are some specific repeating patterns. This is pattern for the X, Y, and Z component, and this is north hemisphere, this is south hemisphere. And to understand why it regularly happens during the daytime, why it's daily patterns. People thought that should be currents in the somewhere above. It's not because of the internal process. It's outside in the atmosphere. And so they kind of create them by using the math, and they found them later in the observations. So these ionospheric currents create magnetic field variations. Equatorial electrojet is a current that flows along the magnetic equator in the E region, and it's created by self-supporting mechanism. First, because of the SQ current, we have eastward electric field along the magnetic equator. So if on this plot, this line is along the magnetic equator, this is vertical, and because we have magnetic field, which is directed this direction, so E cross B drift produce a downward Hall current. So this is Peterson current along electric field. This is Hall current with perpendicular both electric and magnetic field. But these currents create in turn secondary Peterson current upward. And this current in turn create a secondary Hall current, which is flow exactly in the same direction as the initial current. So we have reinforcement of the initial currents through all this process near the equator. And that's why we have this very nice, very continuous electric current that exists through all time. There is no, well, there are of course daily variations, but they are not very strong. Also near the equator, we have a thing called fountain effect. When plasma is from the E layer is lifted upward to the F layer, and there it's diffused along the magnetic field lines to the gravity and pressure gradients, and due to E cross B drift, and create ionization anomalies in the F layers. This is this ionization crests that we already saw on the other figure. They are located at about 10 to 20 latitudes on the both sides of the equator. And they are in the F layer. In the polar latitudes, we have two auroral electrojets. This one. And they are Hall currents, and there are Peterson currents through the field aligned current system, and all of them, of course, interact. And this happens in the D and E region of the polar ionosphere. During the quiet conditions, they are confined to the auroral oval, where the aurora normally observed. But if we have geomagnetic storms, this area expands both to the poleward and equatorward. As I already told, there is a coupling between the ionosphere and magnetosphere through the field-aligned currents, and mostly during geomagnetic storm, to the upper atmosphere with winds, tides, and waves, to the lower atmosphere through gravity waves, and also to lithosphere and ocean through the gravity waves that created by these events and propagates through the atmosphere. And another thing, we already saw this figure. This happens in 2015, in March 17th, this so-called St. Patrick's storm. You see, there was, before storms, everything was quiet. Then there was a storm. And after storm, the ionosphere already recovered. And then on day 20, we have something strange. The ionization started to rise, but at some moment it kind of stopped, and then even started to decrease, and then something kind of reinitiate the process, and we have not exactly the same amplitude, but a good daily cycle. Any idea what can produce this? It's a kind of related to space, but it's not space weather. It's kind of related to sun. Sorry? No, there was nothing on the sun. Sun was quiet. No fires, no storms, no nothing. What? Yes, it was an eclipse. It was seen in Europe at the morning of March of 2015. And exactly at that time, you see, the ionization, when the shadow of the moon covers the sun, the ionization rate obviously decreases, and recombination started to take the free electrons. And we have this even decrease of the total electron content on the moon. And then when the moon shadow passes away, we have a normal ionization rate, but of course, we already couldn't reach the normal maximum, but we still have this. So this is the first way how eclipse could affect ionosphere, but also because moon shadow, when moon shadows the sun, there are gradients in the temperature in the atmosphere, and this creates some irregularities and gravity waves. And we, if they propagate upward, we can find regular changes of the electron density on the huge areas. I couldn't find a nice figure, but during this eclipse in Europe, they also observed some wave-like structure related to these waves. So, ionospheric space weather. Again, we are going to talk about geomagnetic storms caused by CME and CRs, and about solar flares. And also, I will focus on middle latitudes and tech and scintillations. That means I'm going to talk mostly about the F region. So during the storm, at high latitudes, we have particle precipitation and ionization and increase of electron density. Also, we have thermal expansion of the atmosphere because of Joule heating. And this creates upward winds. And upward winds bring to the F layer air rich in molecular nitrogen. So this ratio decreases, causing decrease of the electron density. Also, during this period created equator-bound winds. They move from polar to equator to middle latitudes, and this also caused a decrease of this ratio and decrease of the electron density. In the middle latitude, we have downward winds, so we have more atomic oxygen, and this ratio increases, and we have more free electrons. Also, eastward electric field during things called prompt penetration of electric field and disturbed dynamo-electric field. It's a mechanism that provide electric field propagation from the magnetosphere to the ionosphere. They also, because of the eastward electric field, we have decrease of the F layer altitude, and we have increase of electron density. So during geomagnetic storms, we can have both increases and decreases for electron density because of the balance between different processes that I mentioned here, and there could be other things, smaller things, but this is the main. So they can be positive storms when we have increase of the electron density, and there can be negative storms when we have decrease of the electron density. Sometimes ionospheric storms took place only during the first day of the geomagnetic storm. Sometimes this extended to the 2 days. Like this is the case of St. Patrick's storm in 2015, when in mid-latitudinal station we have a positive storm during the first day and the negative storm during the second day of the storm commencement. Also, the ionospheric storms, its onset of the ionospheric storms, that is strictly related to the geomagnetic storm commencement time. Because imagine the geomagnetic storm happens during the night. In the night, we don't have that much ionization. We don't have that much ionosphere to respond. So that's why response, of course, sometimes we have some variation of the electron density during the night, but in most cases, ionospheric storms start only during the daytime. And this actual, if it's a positive or negative, and for how long, it depends on the season, location, commencement time of the geomagnetic storm, and whatever. And also there is a hemispheric asymmetry that sometimes we see stronger effect in one hemisphere and weaker effect or no effect in other hemisphere. And this is also related to the atmospheric dynamics, how meridional winds flow in each hemisphere. Also, during geomagnetic storms, we can see things like traveling ionospheric disturbances, or TID. They look like a wave-like structure if we plot ionospheric electron density. This is time. This is latitude. So you see we have areas with higher density, lower, higher, lower, and they create wavy patterns, and they propagate in space. So they are not staying, they are moving. They created by waves in the atmosphere, in the upper atmosphere. They can be medium scale, they can be large scale, depending on their speed, wavelengths, and period. And also traveling ionospheric disturbances could be related not only to geomagnetic storm, but to atmospheric variation from atmospheric waves. Flare. Flare is a flux of electromagnetic waves. So when it's hit Earth, it creates extra ionization in the sunlit area of the atmosphere. And if we have a very strong flare, it can significantly increase electron density in the ionosphere, and the radio waves that are normally used to communication, they are absorbed there, and we have a blackout. This is for what happened in 2014, in October 27. We had a, I don't remember which flare, but it's some X flare, and you see the huge area when there should be a blackout for radio communication. Scintillations. Well, if we have a quite normal ionosphere, we have satellites, we have a receiver, we have a theory of wave propagation, we can take care about the ionosphere, we can take care of the troposphere, and we can ensure clear signal and calculation of the position. What the GNSS uses to understand where you're located. But if there are some inhomogeneities in the ionosphere, the electromagnetic wave from the satellite, they passing through the areas of high and low density, and the signal is disturbed in irregular wave. There are changes in the amplitude, sudden changes in the amplitude, sudden changes in the phase. The waves can even come from not right direction, and this causes loss of log, so receiver couldn't continuously keep connected to a certain satellite, There could be problem with amplitude and stuff, and this is called scintillations. What are they caused? They can be caused by TIDs, both atmospheric and scintillation and space weather origin. So we have regular waves, we have regular changes of the electron density, and if signal passing through them, we have scintillation. And if we are in the low and equatorial latitudes, we have things called plasma bubbles, this area of the low density comparing to surrounding, low electron density, comparing to surrounding ionosphere. And this also, if signal pass through these plasma bubbles, it's also experienced scintillations. Scintillations mostly received, obtained, detected by GNSS receivers. They can be phase scintillations. They are mostly seen in high latitudes, and there are amplitude scintillations. And if we study the GNSS signal, we can calculate indices. S4 is for amplitude scintillation index, sigma phi phase scintillation index, and we have calculate the rate of tech, how fastly tech change, and this will be a ROTI or rate of tech index. The different indices can be used to study scintillation on homogeneities on the ionosphere on different scales. For example, this map shows variation of the ROTI, rate of tech index. It was during the storm of June 22-23 of 2015. And during, okay, okay. There have been area of high ROTI values during that evening. They're related to medial scale inhomogeneities in the atmosphere, from units to tens kilometers. They are called mostly by TIDs, not necessary, but mostly, and they can be detected by the ROTI index. On the smaller scale inhomogeneities, to study them, we need S4 and sigma phi indices. If you look in this area, you'll see black circles. These black circles show S4 index variation. They're proportional to amplitude. The size is proportional to S4 index. So these show areas where we have a smaller scale scintillation inhomogeneities, and they are below 100 to maybe 1,000 meters, and they're mostly caused by equatorial plasma bubbles. And this event in June 2015, during geomagnetic storms, we have a spillover of equatorial plasma bubbles to the middle latitudes. They've been observed even near the Canary Islands and Madeira. This is a very rare event, but it happens. The physical sources of irregularities are Kelvin-Helmholtz instability, Rayleigh-Taylor instability. This happens mostly at the equatorial latitudes, and outside high latitudes we can have auroral precipitation, auroral blobs, storm-enhanced density, and other interesting stuff. Kelvin-Helmholtz instability happens when we have a velocity shear. There are two flows in the liquid or in the ionosphere with different velocity, and this different velocity, this shear, cause perturbations and creations of wave-like and vortex-like structures. This happens mostly at high latitude and actually quite rare event. Rayleigh-Taylor instability. Rayleigh-Taylor instability happens when we have a more dense liquid or ionospheric layer with high electron density lying above the low density liquid. When we have this gradient, then instability caused creation of the fume-like structures. So the low density liquid goes up to the high density liquid. This creates equatorial plasma bubbles. This is main mechanism to create equatorial plasma bubbles. So we have areas with lower density inside the areas of the high density. So if this is a E layer with low electron density, and this is F layer with high electron density, so this creates plasma bubbles in the F layer, this mechanism. This very often happens in equatorial and low latitudes, and they initiated after the local sunset. And then these plasma bubbles can survive several hours during the night. Okay. So how these different ionospheric disturbances affect our life? So again, if we have expansion of the upper atmosphere, we can lose our satellite because of the drag. We have ionization, we have radio blackouts and loss of logs. What are examples of these events? So May 1998, there was a malfunctioning of the North American satellite Galaxy 4. Owners of the Galaxy 4 never accepted that it was a space weather event. But analysis of what happens in the atmosphere, in the ionosphere, in the magnetosphere during this period showed that the most probable reason for loss of the satellites was a space weather. There were two CMEs, an X-ray flare, and there was a geomagnetic storm, very strong, minus 200 nanotesla. And also, as I showed before the break, there are two Van Allen belts. But during this storm, a third belt between the two was created. And it lasted until mid-June, so it's more than 1 month. And these electrons in the belt, they can damage instruments and the satellites. And it was not just this satellite, but others that were malfunctioning or lost during this period, May-June 1998. There was a Quater A satellite, Polar satellite experienced communication problems, and 4 Motorola Iridium satellites were also malfunctioning. March 4, 2002, during the battle in Afghanistan, there was a failing of the communication between the operational center, and the helicopter, and they didn't receive a signal in the right time. They landed in the wrong place. They've been under fire. There was casualties, and this was caused by oscillations. There were plasma bubbles in this area. This area in Afghanistan is quite common to have plasma bubbles, and there have been plasma bubbles during this time interval observed, and this caused a very drastic effect. Halloween storm of 2003. During this period, there have been massive problems with communications between the airline and ground controls. It was caused by solar flare, huge solar flare, X solar flare, and also there have been more other flares that keeping ionosphere in disturbed conditions. And all this resulted in communication disruption. GPS malfunctioning. And because people in the in the command ground center couldn't contact airplane crew and couldn't navigate them normally, there've been delays on the plane. Flights were diverted from the polar routes to avoid radiation hazards and to ensure good communication between the ground and the airplane. There have been other non-ionosphere related damages like power outage in Sweden and in South Africa caused probably by jigs. Also, Soho satellite temporarily failed. Soho satellite is a beautiful satellite that observed our sun for already, I don't remember how much years. It was designed to fly for maybe, I don't know, 5 years or something, but it's still going and it's fantastic. It sent us images of the sun every day, many photos, and hopefully we didn't lost it in this storm. Also, astronauts experience radiation hazard. They had to stay in a more protected areas of International Space Station to avoid exposure to the energetic particles. February for year 2022. SpaceX launched a number of satellites. They've been warning that there is small geomagnetic storms during their launch, but they still launched them. They said, small geomagnetic storm, what happens? But because probably normally they probably go away with it, but in this particular condition, something happened and there was a huge expansion of the upper atmosphere. And the atmospheric drag was so huge that they lost most of their satellites because of this, because they sent them to space in the wrong time. Communication problems related to specific events. They are NOAA, it's American Atmospheric Association, American Atmospheric Agency that provide also with another prediction of the space weather events. They have classification for geomagnetic storms, solar events, and radio blackouts. And here there are some very strong events related to radio blackouts because of some flares, also radio blackout and geomagnetic storms. And we have communication problems, navigation problems, again, communication problems. All because the ionosphere was in the wrong condition. Aviation safety depends on GPS, on GNSS, and on radio communication. And so if there is something wrong in the ionosphere and the signal couldn't pass normally, there are blackouts in the GNSS signal, there are control radars couldn't see the flights, they have to send polar routes to lower latitudes to avoid communication problems. Also in Europe there is a European geostationary navigation overlay service which is used to enhance the positioning quality of the GNSS services. It's a specific service. There is one in America, there is one in Europe, I think there is one in Japan or China, I don't remember. And they make airplane positioning system more precise because nowadays it's often that landing is automatic. It's driven by GNSS systems. And if you miscalculate the position of the plane, especially in the vertical. If there is a huge error, you can have a very grave result. So this system is designed to improve the position and quality. And if it's malfunctioning, we have problems with aviation safety. Nowadays, we more and more related to satellites, and so that's why it's important to keep an eye on the ionospheric conditions. Otherwise, not only navigation and communication is problematic, but for example, some modern farmers, they use so-called precision agriculture. They have the trucks passing on the field automatically using GNSS positioning. And if there are some scintillation or some other problems in homogeneity in the ionosphere, the position is wrong, and then they can have losses in the money or something. The GNSS positioning used in oil and gas drilling offshore, in rescue operation, in some emergency services. So if we have problems with this because of the ionosphere, we may have a very drastic effect in our economics, in our life. This plot shows different consequences of space weather events. And if you focus only on the ionosphere, so if we have a flare, radio or X flare, we have wireless interference, radio absorptions, which affect GPS, high-frequency communication, and mobile connectivity. If we have geomagnetic storm, we have ionospheric storm, and ionospheric scintillation that also affect GNSS, space radars, communication satellites, and services. And if both of them accompanied by energetic particles, we have polar radio absorption and problems with high-frequency communication there. And I'll stop there. So, questions? Okay. You can call this authority. Normally, people still more often use the word GPS, but nowadays it's better to say GNSS because, well, now our smartphones and even other navigation devices, they use all kinds of satellites, constellations, not just GPS, which is the oldest one. That's why we often say GPS. But now we have Galileo from Europe, we have Russian services, we have Chinese. Also, there are Indian and Japanese constellations, but so there are many, and depends on where you are and what your software you have on your navigation device. You can use different constellation, and it's better to say GNSS. Yeah?
You show a picture of the non-monetized storm, and my question is, why for the same storm, the same location, the same season, you have a positive storm and then a negative storm?
Oh, like this, yeah?
Yeah.
It happens. Sometimes we have just this one. Or it can be a negative storm. It depends on where you are. It depends on what season. It's in tech. And this is middle latitude. It's Dubers. So if it go to the higher or lower altitude, we may have a different pattern. And if we go in the longitude, for example, the storm in Japan may cause a different storm than it's in Europe, for example, on state. So it's every time we kind of waiting to see what's happening in the magnetosphere, in the how electric field is introduced in the ionosphere, at what latitude when it started, what was the meridional wind direction, and all this stuff. You may say that, for example, in certain areas, you may make historical analysis and say, this type of storms is more often, for example, in middle latitudes, for example, here, we have most often the positive storms, or positive negative. So next day we have a decrease in ionization. But it doesn't mean that we couldn't have a negative storm during the first day. Yeah?
Okay. Thanks for the presentation. Yeah, from the announcement, we have two peaks, if I'm seeing very well.
Yeah.
We have 1, 2, but in the negative phase, there's nothing of such. Could you please show the other events that you show like this? The other diagram, I think you have the other diagram. So just to, if it also has 2 peaks, as we have it in the announcement.
Depends. Sometimes we have just nice peaks. Sometimes we have something normal and then increase like this. Only increasing the altitude. It all depends on how, when the magnetic storms start, how the current of the magnetosphere and how it's projected in the sphere, how it's then goes
to lower latitudes. So it's there is no there is no main mechanism. Every storm is a bit different, and you study and you say, okay, here is because of that, and here is because of this. It's hard to predict. Statistically, yes, but
there are some work that shows that storm with stuff like that.
yeah, but even statistically, we don't have that much material to make a good statistical forecast. Because, for example, you need to take the Cameroon season, probably sort of fake, because decreasing.
Yeah. Thank you.
And sort of in addition, of course, you can have a number of parameters when the solar interface.
So the main thing we should just look at for is the enhancement and then the positive and then the negative phase.
Normally it's post-processing.
Thank you so much.
And for the hospital, are they working on some parallel system that could work when there is this kind of storms? Because you said that sometimes the connections were. Is there a solution to, or there is no system that is going to work?
Well, if you are flying in the plane and your only communication is through
certain radio waves in certain frequencies that are used for this communication. So if you have problems, you try to move from this area and to avoid it, because for ground situation probably we can have some backup system, but it's
But it can have a bigger problematic for hospital, for example, or
yeah. I suppose that those people that that had their flights delayed, or that took more than expected time to fly from their place to destination, they are not happy. And also avia company, they spend money on the fuel, on the extra maybe landing or something. It's rerouting, it's all very strong economical things. Also, I had that some bank operations, they're related on GNSS timing, and this, if there is some malfunctioning, it also costs them money. So, yeah?
You showed how geomagnetic storms is seriously affecting your communication. So my question is there any reporting that lower atmospheric forcing is causing serious problems in the communication. For example, during SSW, it will affect there will be a variability due to the SSW. Yes. So how much serious it is?
Is it low atmosphere?
Yeah. Is there any problem?
Okay, there are studies that show that, for example, if you have a strong, in Asiatic area, if there are typhoons and this kind of very strong events, they're seen in the ionospheric parameters, in the perturbation of the tech. In Europe, we also can see that we don't have these strong storms, but even some strong, our strong storms, they also can affect, the effect can be seen in tech variation, for example. And sometimes they can, if there is perturbations, they create TIDs, traveling ionospheric disturbances from atmosphere to ionosphere, and it's caused. How much problems they can create, I'm not sure, but from the scientific point of view, yeah, they're interesting, they're studied.
One question.
Yep.
There was written that in Sweden there was a big blackout, and then there was also like a plane loss connection. Is it any reason that, maybe Sweden is located in an area that...
Well, I suppose that
This power blackout was because of the GICs, geomagnetically induced currents, which created in the power lines when there are fast changes of the magnetic field, they create currents in the grounded conductors. This one, no, this one. And this also happens in the South Africa during this event. This is GICs, but they are not related to ionosphere, but they have the same cause, the geomagnetic storm and the flares. So they kind of same source, but different effect. Geomagnetic storms are more dangerous in this way because they can create effect there and here and satellites and on the ground and the ionosphere. Flares are more focused on the ionosphere in this case, and a satellite, of course. So, okay.
Because in the south of the as magnetic field is weaker, we observe also stronger effects in this zone when there is storms.
I couldn't say that there are strong effects, but they are, it's a very specific areas. Also because it's quite, because also, because of the anomaly, magnetic equator goes south, and all the plasma bubble stuff, they also follow the magnetic equator, so they kind of, everything happens in the same place. So it's a very interesting area to study, and Brazilian and Argentinian people have a very developed space weather groups and institutions to study all this stuff. Okay?
Yeah. What can be inferred from this claim is other than the information that there exists some structure? So, can you...
Well, what you can see, you can, if you have good coverage or you have more receiver in the area, you can kind of localize this small anomaly, but of course in this case you should be happy, so it's this anomaly is seen by the satellites that are seen by your receivers, so it's, if you have this kind of indices, it's less global view Because for tech, we have too many receivers and we have maps and everything, and we can create roti maps much easier than S4 and Sigma 5. But I think in the polar latitudes, they are studying Sigma 5 more, phase translation more with other instruments because, well, they happen more often, they have more instruments they are located. Okay. Thank you very much. So if you would like to have more of those books, come